and mechatronics. And it's when it comes to mechatronics, we are combining mechanical or mechanics and electronics, hence the word mechatronics. So how are we having these mechanical systems? They need power, they need electrical parts for them to function. We normally have some inputs that maybe, or maybe you can take an example of regulating temperature in a room. So that is a mechanical system, but we need some electronics part for it to function. So we normally have the input, where the input is like we need to sense the temperature within that room. So we need to have sensors which detect or which are able to detect that temperature, and then temperature is converted within, to a certain signal that is fed maybe to that air conditioner, automatic air conditioner. If maybe the temperature is high, there is a value of that signal, maybe in terms of voltage, which now goes to the maybe controller within the system, and there is a command that is already uploaded, and maybe now it can send another command to actuate the system. If it is a motor, to start rotating so that it can cool the environment. So we will see that we have this combination of mechanical systems and also the electronic part of it for our system to be able to run effectively. As you see, we have the control system or the heart of the system, where that control system feeds data to the microcontrollers, the central processing unit, and then we need communication to happen within the various units of that system. And also we can also have, if it's not microcontrollers, we can have the PLCs. So the term mechatronics originated in it's a Japanese origin in 1980s. It is a synergistic integration of three branches, that is mechanical engineering, electronics, and also intelligent computer control, where we need to combine this system and communicate effectively by uploading our commands to those computer systems. And so mostly it's used in design and manufacturing of industrial products and also processes that happen day to day. So as we have said, the main three branches is mechanical, electronics, and also IT, or the computer control. But the disciplines that are covered within that area, we have the mechanics, electronics, IT. Then we need actuators and sensors. Whatever you need to study your environment through sensors, and you need to activate something that will control or meet the objective of what you wanted to achieve, maybe by having actuators. Those are motors. But before you build your system, you have to do the design or modeling and also simulation, something that running on the software. After that, then you build your hardware system, and then you can test in real time, or you can do your tests and validations. So this is just an illustration of the same concept of mechatronics. So we have said we have mechanics, electronics to make mechatronics, but for a system or for that system that you are building, you want to build for it to perform, or the system that we have to, for them to perform, we need actuators, sensors, and so on. You have to model and simulate before you build your hardware system, and also you have to do testing and validation. So this is a closed loop of a mechatronic system. As I said, we have actuators, sensors, then the system, the processes happening within your mechatronic or mechanics or that gadget. And mostly all these processes happening is more of energy conversion from one form to another. And whenever it's in a certain form, it's read as a certain instruction to that system. So we need to monitor variables using sensors or transducers. They move from one unit to another, and so we can be able to achieve a desired output. So the first thing you need to do whenever you're building a system is to understand the components that are required for that system. Measurements, the aim is to have accurate, precise, and repeatability. If it is a sensor and you want to build a system, you want to be sure that it will give you accurate results, precise, and also if you are to repeat uh, function again, it will still give you the same results. It will not now behave in a different manner. So, but however, since we cannot have an ideal kind of product, they still come with some errors, and mostly we have two types of errors, that is bias and also precision error. And a bias error, we normally have also a calibration, or it can be divided into two: calibration and loading errors. So mostly also in whichever gadgets that we normally use, they normally have to go, for you to acquire accurate result, we normally do calibrations, and we have calibration centers that you can go and try to calibrate your whatever kind of machine that you have. If it is a weight machine or whichever kind of machine, you can do calibration and identify whether there is an error or there is no error within your system. And if there is an error, you know by what margin. So you need whatever result you get, you need to add or subtract the error that you have. So one of the systems that we have uh, in electrical is the Wheatstone bridge circuit, which is used to measure or to determine resistance values essential in strain gauge application. So you can have a material, you don't know its resistance, its resistivity or its resistance, and maybe you want to know before you apply in strain gauge. So we normally have the Wheatstone bridge circuit where you have like uh, four areas of resistance or value of resistance, and then one will be unknown where you normally apply your put your material, and then through the Wheatstone bridge rectifier, the output voltage is how you calculate, and so on. You'll be able to find the resistance of that material, and also you can be able to find the strain gauge after getting the resistance of a certain material. So this is the circuit, the Wheatstone bridge circuit. It normally has the four resistance balanced in that manner. And then now one of the resistance is normally unknown, where you now put your material that you're interested to know its resistance value. And then after the calibration, they are used, you can be able to calculate or to know the behind the scenes, the one principle of which how we are able to attain that value through this formula, the output voltage. From there you get your unknown R, and then whatever you get now with the constant given, you can find the strain of the system. So Wheatstone bridge is an example of the measuring units that we normally have. So these are the application of the Wheatstone bridge. You can determine the absolute resistance value, relative resistance changes, strain gauge measurement, signal conditioning in sensors, and also the pressure and force measurements. Also, for a system accordingly, we have said sensors help us to detect or to do measurements which function mostly as the input to our system. Remember, for any system we are developing, we must have what is the input, then we have control happening, and then we have an output. So what is the process happening? You have already fed the input, which has been monitored or detected by sensors or transducers. The different types of environment, what are you interested in? Is it pressure, force, strain, temperature, humidity, all that? So we have processing that happens, and now we can say within the processing is a control system and also mathematical modeling. Remember, we said you need to do design. What happens inside that processing? The signals that are coming in as input, what happens? So we normally have two different types of control system, the open loop and also the closed loop. And the open loop, we don't have the feedback mechanism. So we can either start with this to see this is the open loop system where you don't have a feedback. Whichever output you get, that is the output. But for the closed loop, we still monitor the output. Did we meet our objective, or that is what we are taking back? The feedback brings back that output figure and compares with the set. Compare that output to the set parameter. If we have not achieved our goal, then the process continues until we achieve the right parameter. So for open loop, we don't have that advantage of getting the feedback of the output that we get from that system. So for open loop, we can say there is no feedback. It is simple and inexpensive because of they lack that feedback loop, and also it's less accurate. It's less accurate because we have said we don't have the feedback, or we are not the output is not being compared again with the set amount value. So example of open loop system is a toaster, a washing machine, timer, and so on. On the other hand, the closed loop uses a feedback. We normally have a feedback loop. It's more accurate and stable, and also self-correcting because we are able to compare the output to the set parameter. Example of this, we have the thermostat, the cruise control, and so on. So the closed loop can use the PID control, that is the proportional integral derivative kind of actions. We can either have the proportional action alone on its own, integral action on its own, or derivative action on its own, or we can combine all the three when having the closed loop feedback system for it to be more effective. Remember, for this PID to function is where we are trying to study the output in relationship to the input until we find the right, we meet our objective. So it's where we normally have to calculate or to work on the transfer function, where transfer function is the output, is the ratio of the output divided by input. And transfer function is where we normally, for us to be able to model it effectively, we normally use Laplace output or transformation, where we either integral or derivative, and we equate that equation or that ratio to zero for us to obtain the right um the what that word optimal, sorry, the optimal value of that system. The optimal is the most efficient or less cost or the best results that you can get out of that equation. So mostly those systems you find in the closed loop or both, or even open loop, we normally have the transfer function, and mostly is a function of the output divided by the input. And further, we use the Laplace transform and you equate to, or you start with zero initial conditioning, or when you are doing the either derivative or the integral, you find or you make the equation equal to zero for you to find the optimal value of that system. So you can be asked just general or compare the open loop and closed loop system. Those are the three key parameters. So as we said, this is an example of open loop, and this is an example of closed loop. And closed loop can either have uh, the proportional action on its own, proportional action and integral action, or the three combined, where we have even the derivative action controllers in the system. Again, we can also modes, adaptive control, and so on for it to be more effective. So I will also share a detailed um, PDF of this note where you can refer if you want more details of these uh, subtopics. But mostly also you will find that these are more of combined units that you have studied before. For example, this closed loop and open loop system, I think you have covered in another. I don't know which unit, but mostly maybe you find them in thermodynamics, but I'm not sure. Actuating systems and motors, electrical machines, which you covered. Then we have microcontroller and microprocessor. I think you have done a unit in microprocessors and so on. So those are the controllers. We have open loop and closed loop. And then after the processing, we need to have actuators in the system. So if it is What are we regulating? If it is temperature, if it is a fan that is automated, we need to actuate, we need to switch on a motor that will make it start, that fan to start rotating for us to achieve the desired output. So mostly the actuating systems are more of motors. Mostly motors are the ones that are used in most of the system. If it is a position, maybe the whatever position we want for a shaft to face in a certain position, we use maybe a motor to rotate it until we fix it in that right position, and so on. So we have different types of motors. We have AC and also DC motors. Under AC, they run on alternating current, and we have two types, that is synchronous and induction motors. For synchronous, the speed of the stator and that of the rotor are the same. For induction, the rotor moves at a lesser speed compared to that of a stator. The difference is because of the losses that happen between the stator and the rotor, the air gap losses. We also have the brushed DC, where the coils are in the center rotate around permanent magnets. So the coils are the one which are the rotor part, and then the stator part is the permanent magnet. So it is simpler in construction, but now because of the coil rotating, they require maintenance of those uh, brushes because of the friction. Then we have the brushless DC motors. Magnet. The permanent magnet is now the one which is rotates, which is makes the rotor, and then the coils are the stationary part, the stator. They have better power to weight ratio, and also they have high efficiency and reliability compared to the brushed DC. Then we have a stepper motors, which is an extension of a brushless type of a DC motor. Mostly stepper motor, they don't rotate continuously, they rotate in steps. You can find maybe one that makes steps of 60 degrees. So it will, for a complete cycle, it will make 6 steps. You can have another one for 30 degrees, 15 degrees, or in that manner, depending on the application. And mostly you find most robots normally use the stepper motor as they move in steps. Those steps, or if it is rotating, it makes does not make just a complete rotation but in steps. So we normally have those stepper motors. So mostly, as we have said, we can use for actuating system, we can use any motor or whichever fits your kind of system that you are building. Then you can know which kind of a motor to use. And also using the power electronics, you know, if you have a DC motor, you know the kind of power to connect to it. So I said we also need the heart of the system, the central. We have output depending on the instruction or the command that you give using the programming language. 1 minute. Yeah, depending on the instruction that you are given, you have an output. So we need communication between these blocks, input, a processor, output, feedback, and so on. There must be communication that is happening. And so either communication within the system that you have built and so on. Another communication example that you can imagine is how do we communicate with our phones and so on. Between you and the receiver and communication happens. So within the units or the blocks that we build within a system, how do they communicate? So we normally say there's a sensor communication and also the network around your system. So we normally have the serial transmission and also the parallel transmission. And these are the how different the two are. So for the serial transmission, we normally have the CAN bus uh, and USB, but for parallel transmission, we normally use the GPIB or the IEEE 488 kind of communication, or the bus at all the, do we say it's like the wires for that communication to happen. Then for serial transmission, we have it's a bit by bit along a single line. But for parallel transmission, we can either do 8 bits, not one at a time, but it can be in multiples of either 8, 16, or that 2 bits simultaneously. For serial transmission, only two conductors are needed. For parallel transmission, it's a separate wire for every bit. So serial communication is slower because you can imagine we only require only two conductors at a time. But for parallel transmission is faster. So still under this serial transmission and parallel transmission, we can have different transmission modes, either simplex, half duplex, and also full duplex. Simplex is only when you're communicating in one direction only. For instance, a printer, we can only communicate from the computer, give instruction, print this paper, but you can only not receive a command from the printer to the desktop or to the laptop. It's only one way. Half duplex is where you have communication both ways, but one at a time, one direction at a time, which is switchable. For instance, the CB radio. Full duplex, you can have both direction and they can happen simultaneously, e.g., a telephone or a mobile phone or whatever. So when we talk about mobile phones, when it comes to the network system of such communication, we normally talk of something that is called the OSI layer, or it has 7 layers. So maybe this one you can look into details or you can Google the model and you are able to understand what each and every area means. So physical, or if you go to telecommunication network, this is the basic model or the fundamental model of such networks of telecom. So we normally have the physical, the first layer is the physical, then data link, network, transport, session, presentation, and then the seventh one is the application. But this is how these different blocks that we are talking about, or from one system to another system, what is the network behind those systems? Or if it is whatever we are talking about, the local area network, then you can have a wide area network. How does that communication happen between those the different networks that we have? Then for these systems to function, remember they don't understand the human language, we normally have to use their assembly language or different languages that they do understand. So there are four steps of PLC operations. We have the input, scan, detects the state of all connected inputs. We have different inputs from different maybe sensors or monitoring units. Then we need to scan these inputs that are coming in. Then we have to process them, program scanning, and then give a command or an output where you either energize a certain system or de-energize a certain system depending on what was the input. Then you need to do housekeeping or to test the output or validate the results that you are getting. So the PLC programming languages, you can either have ladder diagram, structured tests, instruction lists, sequential function chart, function block diagram, and so on. I don't know whether you have covered PLC. If not, maybe you'll be covering it in your final year. So for instance, if you are using an Arduino, which is an open source microcontroller platform, mostly its input must be 5 volts DC direct current. It has a clock that is 16 megahertz. It normally have a number different pins. 6 are analog and 14 are digital input and output. It can either, if you're using the board, you can either have the USB or the FDTI cable. Yeah, sorry for that. So we are saying in PLC we have the different languages that you can use when working on a PLC. Yeah, programmable logic controllers. Yeah, then still these systems we normally use either digital logic or number system where we can either have binary or the hexadecimal systems. They don't understand our number system, and so they either understand the digital logic system, and where we have sorry, we have the digital logic, and also we have their number system where it's binary and hexadecimal. For digital logics, which you did in is it electronics or digital electronics, remember we had the and, where it's only give an output of 1 if all the inputs are 1. So if it's more of like multiplication, like remember it's a binary, it's either 0 or 1. So we can only get 1 if both the inputs or all the inputs are 1 1 1 1. If there is a 0 in a certain area, then the output will be 0. Whenever you multiply a number by 0, it will give a 0. Then we normally have the OR. So long as there is one input that is 1, then we have an output of 1. So long as the inputs we have 1 somewhere, it's more of addition. 1 plus 0 0 0 or 1 plus 1 in a binary system, then it gives a 1. So not invert the input signal. So if input is 1, then the output, if it is a not logic gate, we have a 0 and so on. We have the NAND, which inverts the AND. You have the NOR, which inverts the OR, and XOR, where output 1 when inputs differ, and so on. So the number systems can either be binary, for example, binary uses 0 and 1, or it can be hexadecimal, where you have 0 to 9 and then 10 to 16, that is A to F. For instance, if this is a binary number, and if you are to convert it to our number system, then that gives you 22. So this is 0, 1, 2, 3, 4. If you are to calculate this to give you 22, it will be 1 times 2 raised to power 4. 2 raised to power 4 is 16. Then 0 times 2 raised to power 3, that will be 0. Then 1 times 2 raised to power 2, that is 4. 16 plus 4, 20. Then 1 times 2 raised to power 1, that is 2. 20 plus 2, 22. Then 0 times 2 raised to power 0, then is 0. Then the result is 22. You can either have another number and you are able to convert it to a decimal number. Then you have the hexadecimal, that is H for hexadecimal, B for the binary. Then A3E, that is 26, 22 if you are to convert it to a decimal system, and so on. So we can have such an example of DSC, DSC example where you are given an 8-bit R to R, and then the reference resistance is 2, reference voltage is 10 volts, input you are given in binary form, and or with this other number system, then what is the output. So you have to convert this binary to a decimal number, and so you can be able to find the voltage from whatever you are given, the values that you are given, and so on. If it is an 8-bit, then you know it will be more of a 256 kind of RAM, and so on. So we have a key review questions that can maybe guide you through the notes. Define mechatronics with the need of a neat sketch, the first rides, and so on. Do a Wilson bridge, you have it. Compare SCADA and against DAQ, and define signal sampling, and so on. I will send this PowerPoint and also the PDF that I summarized to us for us to get these notes, and then from the PDF you can be able to answer these example questions. So that is the last slide that we have for today, and also I don't expect for us to be working on any other area. So most probably next week you also get to meet physical. We brush through the power electronics part, and then the other week we can have, after next week, the other week we can have a physical, the second cut, which will be sitting cut, the first week of May. I hope you are okay. Unless there is a concern. If there is no question, I wish you a good night.